Let's talk about matrix multiplication. Let A equal 1, 2, 3, 4, and B equal 5, 6, 7, 8. Find AB. AB is calculated in this way. We basically take the dot product of rows of A with columns of B. So for example, the first row, first column of AB is going to be the dot product of the first row of A and the first column of B. It's going to be 1 times 5 plus 2 times 7, in other words, or 19. First row, second column of AB is going to be the dot product of the first row of A and the second column of B. So that's 1 times 6 plus 2 times 8, in other words, 22. If you want this entry, second row, first column, that's going to be the second row of A and the first column of B, 3 times 5 plus 4 times 7. And in the same way, if you want this entry, it's going to be the dot product of this row, the second row of A, and the second column of B, 3 times 6 plus 4 times 8. So we end up with 19, 22, 43, 50. Let's take A and B being the same, find BA. BA is not the same as AB. BA is 23, 34, 31, 46. Note that AB does not equal BA in this example. Matrix multiplication is not necessarily commutative. Let A equal 1, 2, 4, and 2, 6, 0. And B equal 4, 1, 4, 3, 0, negative 1, 3, 1, 2, 7, 5, 2. Find AB. Oh my goodness, what an ordeal. Okay, so again, A is going to be again, first we do rows and then columns. A is a 2 by 3 matrix, and B is a 3 by 4 matrix. You can multiply these together because these two numbers are the same. If they were different, you wouldn't be able to multiply them together. The result is going to be a 2 by 4 matrix, so AB is 2 by 4. So again, to get the first row and first column of AB, we need to multiply together the first row of A and the first column of B. Take the dot product, 1 times 4 plus 2 times 0 plus 4 times 2, etc. And then to get the other rows of AB, to get the other columns in that first row, we'd have to take the dot product of this first row of A with the columns of B. And then to get these entries down here, we would have to take the dot product of the second row of A with the columns of B. So for example, if you want this entry down here, it's going to be the dot product of 260 and 402, which is 2 times 4 plus 6 times 0 plus 0 times 2. And that turns out to be 12, 27, 30, 13, 8, negative 4, 26, 12. Let A and B be the same as before. Find BA. Oh, you can't. It's undefined. If A is an M by P and B is a P by N matrix, then AB is an M by N matrix. But yeah, you can only multiply them together if this entry of A is the same as this entry of B. In other words, if the number of columns of A is the same as the number of rows of B. Let C and D be two matrices. Does C plus D squared equal C squared plus 2CD plus D squared? Not necessarily. When you multiply this out using FOIL, you get C plus D times C plus D, which is going to be C squared plus CD plus DC plus D squared. Now, this equals C squared plus 2CD plus D squared only if 2CD equals CD plus DC, which means that CD equals DC. In general, this is not true. What would we call this matrix? It's called the zero matrix, and we just denote it with a 0. Let I equals 1, 0, 0, 1. A equals 1, 2, 3, 4. Find IA. When you multiply these together, you find that IA is the same as A. That's why I gave this name I to the matrix. I is the 2 by 2 identity matrix. Sometimes we designate this as I2. IA equals A for any 2 by 2 matrix A. AI equals A as well. Let's talk about some properties of matrix multiplication. Cancellation laws are not necessarily valid. AB equals AC does not imply B equals C. AB equals 0 does not imply that either A equals 0 or B equals 0. One way to solve the equation AX equals B is to multiply both sides by a matrix that turns A into I, so that the left side is IX, which equals X. This matrix would be the inverse of A. In general, the inverse of an n by n matrix A is the matrix that we denote with this symbol. We call this A inverse, such that A inverse equals A inverse A equals the identity. So in other words, the inverse of A is what you have to multiply A by in order to get back to the identity. The inverse of A equals ABCD. Turns out it's A inverse. It's 1 over AD minus BC times this 2 by 2 matrix, D, negative B, negative C, A. And if AD minus BC equals 0, then A has no inverse. There's a special name for AD minus BC, this quantity here. The determinant of the matrix ABCD is AD minus BC. So we denote the determinant of the matrix ABCD. We represent the determinant this way, or sometimes like this. So in other words, it looks like a matrix, but it doesn't have the little, it doesn't have the little hooks on here. So they're not brackets. They're just vertical lines. Let A equal 1, 7, 2, 9. Find the determinant of A and A inverse. Okay, the determinant of A is going to be AD minus BC. So AD, that's 1 times 9, minus BC. So that's going to be, well, BC, you're multiplying together 2 and 7. So 1 times 9 minus 2 times 7, that's 9 minus 14, negative 5. So the inverse, as we've seen before, is A inverse. It's 1 over the determinant of A times D, negative B, negative C, A. In other words, it's 1 over the determinant, 1 over negative 5, and then we switch the roles of D and A. So in this case, this is A, this is D, so you flip the D up here, put the D down, the A down there, and we end up with, the D's up here and the A's down here. And then notice we just stick negative signs in front of the C and the B. So instead of 2 and 7, we just have negative 2 and negative 7. Okay, so it's 1 over negative 5 times this matrix. In other words, when you multiply it out, you get that. So that's A inverse. We'll see a little later how to find the inverse of a 3 by 3 or larger matrix. Consider the system of equations x1 plus 7x2 equals 5, 2x1 plus 9x2 equals 15. Solve the system using matrices. We can represent this system of equations as a matrix equation. So 1729 times x1, x2 equals 515. We've seen that before. Let's say this is ax equals b. In other words, this is our a, this is our x, and that's our b. Multiply both sides on the left by A inverse. A inverse we've seen before looks like this. Here's what we got. Okay, multiply both sides on the left by A inverse. We know what happens here. When you multiply these two together, you just end up with the identity matrix. You multiply these two together, you end up with this. And when simplified, you just end up with, okay, we know what this is. 1, 0, 0, 1 times x1, x2. That's just going to be x1 times x2. And when you multiply out the right side, you end up with 12, negative 1. Look at that. By multiplying both sides on the left by A inverse, we were able to find the solution to this. The solution is x1, x2 equals 12, negative 1. Here's some matrix inverse rules. A inverse inverse is A. AB inverse is B inverse times A inverse. Similarly, ABC inverse is C inverse B inverse A inverse. Matrix multiplication, let's talk about that. The transpose of a matrix A is the matrix we obtain when we interchange the rows of A and the columns of A. We denote it by A transpose. This is not A raised to the power t. I know it looks like A to the t, but it's not. I know that notation's ambiguous. Sorry about that. It's A transpose. So let A equal 1, 2, 3, 4. Find A transpose. Again, A transpose is what you get when you interchange the rows and the columns of A. So the columns become the rows. A transpose is 1, 3, 2, 4. Let B equal 1, 2, 3, 4, 5, 6. Find B transpose. The transpose of a 2 by 3 matrix is going to be a 3 by 2 matrix. That's what we end up with. And here's some transpose rules. A transpose transpose is A. A plus B transpose is A transpose plus B transpose. For any scalar k, Ka transpose is K times A transpose. AB transpose is B transpose A transpose. A transpose inverse is A inverse transpose. And lastly, recall that the trace of an n by n matrix A is the sum of the entries along the main diagonal. We denote it by this symbol. That's the trace of A. So for example, the trace of A, 1, 2, 3, 4, is 1 plus 4. In other words, 5.